In today's activity, we're going to be looking at exponential patterns and functions and their graphs. So we're going to actually start with this, this problem. Ramon Hall, a graphic artist, needs to make several different sized draft copies of an original design. His original graphic design sketch is contained within a rectangle with a width of 4 centimeters and a length of 6 centimeters. Using the office copy machine, he magnifies the original 4x6 design to 120% of the original design size and calls that his first draft. And then his second draft, he does 120% of that first draft, and each new one is 120% of the previous. So let's think how we can do 120%. Well, 20% would be 0.2. So if I wanted to take 4 centimeters, and 120% of that would be multiplying by 1.2, because I'm increasing it by 20%. That would give me, see, that would be a 4.8. And then if I took that and multiplied by 1.2, I'd get 5.76, and then 6.912. And hopefully you are following along with your own calculators. 8.2944. And then I believe this is 9.95328. And then do the same thing for the length. So we start with the original length of 6 and multiply by 1.2 and so forth. So if you can fill in that other side, so the resulting draft for each number of 120% magnifications is a unique width and a unique length. Thus, we could have a relationship between each of those. So let's start by plotting the magnifications as our x coordinates and the width as our y coordinates on the graph over on the right side. We'll make a graph over on the right side. So if I were going to make a graph of this, that's going to be my y-axis, and this would be my x-axis. So on this x-axis is going to go my number of magnifications, the n. So it starts at 0, 1, 2, 3, 4, and 5, and going up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, going all the way up to 15. So starting with the number of magnifications and the width, so this ordered pair. So when we were at 0, before we did any copying, was at 4 centimeters. The first magnification was at 4.8. The second one went to 5.76. The third one is at 6.9. The fourth one is at 8.29. Whoops. third one was at 6.9. It's right here. 8.2 would be here, and the fifth one is 9.95. So for the length, started off at 6, and I'm going to use a different symbol. Let's make a little X. 8.64. Second one was 10.38. The third one, oh, whoops, I'm sorry. Mark those in the wrong spots. 7.2. There we go. And if we look at those, they're not exactly linear. They're not in a straight line. They're kind of curving up a little bit. And I want you to think about why that is happening. Well, in a linear function, aren't you adding the same thing each time? Having that rate of change that is constant. So let's look at some other tables of data. On the next page, and see if these are linear or not. Now, linear functions, remember, linear functions have a constant rate of change. The change in y over the change in x is constant. So let's look at these tables. From 8 to 5, we're going down 3, and we're adding 2. Down 3, adding 2. Down 3, adding 2. Down 3, adding 2. So notice that the change is the same each time. Our change in y over our change in x. Now remember, in an equation, that change in y is our slope. So what would be an equation that represents this? Well, our change is negative 3 over 2x, and the b is your y-intercept. That's happening right there when x is 0. So it's halfway between those 2 points. So halfway between 5 and 2 would be 7/2. Now let's look at the next table. This one's going up by 4, and this side is going up by 3. Up by 8, and up by 6. Up by 8, and up by 6. Up by 12, and up by 9. Notice that the rate of change is still the same. 4 to 3 is the same as 8 to 6, which is the same as 12 to 9. So this one, our slope or our rate of change is still 4/3. Now what would be our y-intercept there? If we went back 2 steps. Well, one way you could find it is if you know your slope and you know an x and a y on that graph, you could plug it in and find that y-intercept. So let's try that. Let's plug in 3, 2. So 2 would go in for our y value. 4/3 of x, whoops, this was a 3, plus b. 3 equals 8/3 plus b. Subtract 8/3, but I better make this 9/3 minus 8/3. Gives us our b. Oof, hard to write on here. Gives us our b, which would be 1/3. Next table. This one, if I was following that same pattern, I'm subtracting 12 here and going up by 1, subtracting 6 and going up by 1, subtracting 3 and going up by 1. So this one does not have a constant rate of change. But what do you see? Well, I hope you see that we're actually dividing the same things each time, or that they're half of the previous y values. Now let's consider the data in the table created in item 1. We're going to copy the width values into this table. So we had 4, 4.8, 5.76, third magnification was 6.912, 8.2944, but I'll just leave it like that. And then we had 9.95. So we're not adding the same thing each time. They're not half of each other. What's happening, remember that we're multiplying by 1.2 each time, because we're increasing by 20%. When you're multiplying by the same thing each time, what we end up with is an exponential function. Whatever we're multiplying by is considered our exponential factor. And you could have two kinds of factors. A decay factor would mean we're going down each time, or a growth factor when we're multiplying by something that's increasing us each time. So in that table of the widths, our exponential growth factor is 1.2. Now remember, the rate that we are increasing by was 20%. It's 20% bigger than it was before. 100% would mean no change whatsoever. And just to think about that, what if we were multiplying by 1.5? Well, 1 would mean we wouldn't change at all. This would be increasing by 50%. But what would be different if I was multiplying by 0.8? That's 80%, right? 0.80. 100% would mean we're not changing at all. This would be a decrease of 20%. Now let's figure out how to write the equation for this. Remember, we started with 4, and we multiplied that by 1.2. Then we multiplied that by 1.2 again. And then we multiplied by 1.2 again. And notice we're going to keep doing it, multiplying by another 1.2 each time. Now that would get a little time consuming to keep writing it out. So what's another way to write repeated multiplication? Well, this would be 4 times 1.2 to the fourth would mean the same thing. This would be 4 times 1.2 to the third. 4 times 1.2 squared Four times 1.2 to the first would give us 1. But if I kept following that pattern, that would mean this would be 1.2 to the 0 power. Now remember, what is anything to the 0 power? It's just 1. So 4 times 1 would give me that 4. So the fifth magnification would be 4 times 1.2 to the 5th power. So if we wanted to go all the way to the 10th magnification, we would just go to the 10th power. So our rule is going to be 4 times 1.2 to whatever magnification level we wanted. So that function for the width as a function of the number of magnifications would be 4 times 1.2 to the nth power. So if we want, if we wanted to find the 11th magnification, so we're finding the width for the 11th magnification would be 4 times 1.2 to the 11th, which if you round up would be 29.72. So let's think about what all these parts are. What was that for? Well, that was that initial value, right? And where did the 1.2 come from? Well, that was that growth factor. It's what you're multiplying by each time. So, in a blanket exponential function, they're always written like this: a times b to the x. So following that rule, a is always going to be the initial value, which in our case was the initial width. And b was that growth factor. Or it could be the decay factor if it was getting smaller each time. But it's what you're multiplying by each time. So in ours, that was the 1.2. So how could we express the length as a function of that magnification rate? Well, what did we start with? The length started at 6 centimeters. And again, our growth factor is 1.2 because that's what we'd be multiplying by each time. Now, what if instead of increasing it by multiplying by 1.2, each one will be reduced to 90% of the previous size? So for 90%, we would take 4 times 0.9. So that would give me 3.6, 3.24, 2.916, 2.6244, 2.36196. So notice that we're decreasing because it's 90% of the size. So for 6, when we multiply by 0.9, we would get 5.4, 4.86, 4.374, 3.9366, 3.294. So think about what's happening here. We're decaying, and what is the decay factor? Well, the decay factor means what you're multiplying by each time. The decay factor is going to be 0.9. But what are we decreasing by? So the decay rate, if we only have 90% of our original size, then our decay rate is 10%, has been decreased. So what would be a function for those? Well, the width, again, started with 4, but this time we were multiplying by 0.9 each time. The length started at 6 again, but this time we were multiplying by 0.9 each time. So how would we find the 10th reduction? Well, you would just plug in 10 to each of those functions. So that'd be 4 times 0.9 to the 10th, which would be 1.395. And the length at the 10th reduction will be 2.092. So if we compared the two graphs for length, and you could use your graphing calculator to graph this. Now make sure that you're careful about using on the graphing calculator, you would do 6 times 1.2, and then you're going to press the up arrow or the caret button to get to the xth term. So the one that we had graphed before, if you look at it on the calculator, it's actually going to do something like this. Now notice before we did any magnifications, this was at 4, right? So our y-intercept was at 4. Oh, I'm sorry, on this one we're doing 6. For the decay one, if you look in your calculator, this time you should see something more like this. This one's going to be the decay, while this one was the one that was growing. Notice that it keeps going up and up and up each time. And this one's going down, down, down each time. But how far down will it go? So let's think about that first one again. What is the domain? Well, the domain is all real numbers. So x is an element of all real numbers. But what is our range? What kind of lengths are we getting out? Can they ever be negative? Can they ever actually get to 0 if you keep multiplying by something? No, y is always going to be greater than 0. On our decay graph, which is a decreasing function, again, we can plug in any x value we want, but we're only going to get outputs of y's that are greater than 0. So again, we said this one was the growth, and then we had the decay. So another way we can talk about this is whether they're increasing or decreasing. If it's going up as you go to the right, then you are increasing. And this one would be decreasing. some graphs do both. Like, think about a parabola. It starts off decreasing, and then it turns to increasing. But these stay increasing or decreasing the whole way through. Let's talk about the end behavior. Now, we know how to write end behavior. We write each side of it, so let's review that. So we're going to start with the end behavior as x approaches positive infinity, so that right side of the graph. So we're talking about the right side. For the growth function, the one where we're multiplying by 1.2 each time, we would say as x approaches positive infinity, what is it doing on the right side? Well, it keeps growing and growing and growing. So y also goes to positive infinity. On the decay graph, as x got bigger and bigger and bigger, our y values got smaller and smaller and smaller. Now, they didn't go all the way to infinity or negative infinity. They get smaller and smaller and smaller, and they almost go to 0. On the other side of the graph, the left side, if you look back at our growth function, as x gets smaller and smaller and smaller and smaller, our graph is decreasing on the left side, but it's only going to go so small. It's only going to go to 0. On the decay function, if you look at the left side, the y's get bigger and bigger and bigger, and they go to infinity. Now, when we get really close to that x-axis, we have what we remember as an asymptote. So this one has a horizontal asymptote at y equals 0. And this one also has a horizontal asymptote at y equals 0. Now let's look at our x and y intercepts of each graph. On the growth function, we did have a y-intercept at 6, because that was before we made any magnifications. But what about x-intercepts? Well, since it never actually touches the y-axis and the x-axis, there are none. In the decay function, the y-intercept is also the same. They crossed at the same point. But our x-intercepts are none. So thinking on just the blanket function, a times b to the x, when will a function increase and when will it decrease? Well, we saw that it increased if a was greater than 1 and b is greater than 1. We know here when b was a fraction or between 0 and 1, we're going to get this. What determines the value of the y-intercept? Well, that was a, wasn't it? That was our starting point. And our horizontal asymptote, no matter what, was y equals 0. So let's look at a couple of other graphs. And a very easy way to do these is to make a quick little table. Easy points to plug in are -1, 0, and 1. So if we look at this first one, 1/2 to the x. So if I take some x values, I'm taking 1/2 to the x. Well, if I take 1/2 to the -1 power, and if you look at your table, you'll see this very quickly. It's going to do the reciprocal and give us a 2. 1/2 to the 0 power. Anything to the 0 power is going to give us a 1. And 1/2 to the first power is going to give me 1/2. So when x is -2, we're at 2, 0, and 1/2. And we could get some more points if we wanted. Straight from your calculator. And remember, it's going to have that asymptote there. It's not going to go past our x-axis. Now, what happens when we have a 4 in front? Remember, that really means we're going to be multiplying by each of those y values by 4. So it's a stretch of 4, right? So that was what we called a vertical stretch by 4 to that parent graph. The next one, 3 to the x. So if I make my table again, x and 3 to the x. -1, 0, and 1. 3 to the -1, that's 1/3. 3 to the 0, that's a 1. 3 to the 1 is a 3. So here is an increasing parent graph. That's what that is called, is a parent graph. Now what's going to happen when I do -1/2 of that graph? Well, the negative, isn't that going to flip it? And a vertical shrink by 1/2. In other words, we're taking half of all of those y values. So instead of a 1, we'd be at half, but we're flipping it, so that'd be -1/2. Instead of a 3, it'd be 1.5, but we're going negative. So you end up with something that looks like that. On our next one, our parent graph is 2 to the x. So you can use your graphing calculator if you'd like, or make a quick table, x and 2 to the x for our parent graph. And I might add a couple more onto here, -1, 0, 1, and 2, because this one's easy. 2 to the -1 would give me 1/2. 2 to the 0 is 1. 2 to the 1 is 2. And 2 squared is 4. So we have an increasing graph. Now, describe to me what's going to happen when I do 2 to the x minus 3. Notice that I'm subtracting 3 from the x. Can we predict what this is going to do? Well, it's going to move us right 3. So each of these points is going to move over 3 steps. Now, on this problem, we also were asked to find the equations of any asymptotes. So on the parent graph, just 2 to the x, we have a horizontal asymptote at y equals 0. What about our transformed graph, 2 to the x minus 3? Well, this graph also has a horizontal asymptote at y equals 0. It's not passing that boundary. The next one, our parent graph is 1/3 to the x. And if we do that to the negative 1 power, that's going to be the reciprocal. That's going to give me a 3. 1/3 to the 0 power is going to give me a 1. And 1/3 to the first power gives me a 1/3. So this one is going to look more like this. Let's go ahead and give its horizontal asymptote. That parent graph always has the horizontal asymptote at y equals 0. Now what's happening for g of x? Well, g of x is taking that parent graph and subtracting 2. So what's going to happen to the graph itself? It's going to move down 2 spots. Each of those points is going to go down 2 places. So what does that do to my horizontal asymptote? Well, it also shifts down 2. So our horizontal asymptote is now going to be at y equals -2. So on this next problem, we have g of x equals 3 to the x plus 4 plus 1. So what would be the parent graph of that? The parent graph would be y equals 3 to the x. And let's sketch that parent graph on our paper. Three to the -1 is going to be 1/3. 3 to the 0 is 1. 3 to the first power is 3. We're also asked to give the domain and range in the equation of any asymptotes. So the domain of this function is all real numbers. And you can write all reals if you'd like. Or remember, we did the fancy r's. And our range are all the y values greater than 0. And we do still have a horizontal asymptote at y equals 0. Now what happens to this new graph? Well, what is the x plus 4 going to do to the graph? Well, that's going to move it left 4 and up 1. So if I take each point, 1, 2, 3, move it left 4, whoops, and up 1. I forgot to move it up 1. 1, 2, 3, 4, and up 1. Does that change the domain at all? Well, it's still going to keep going on forever. So the domain stays the same. What does it do to our range now? Well, it shifted everything up 1. So y is now greater than 1. That means my horizontal asymptote is at y equals 1. Because Oops, it's supposed to be a 1. Because I shifted up 1. The next one, what is my parent graph? The parent is y equals 1/3 to the x. When x is -1, we'll be at 3. When x is 0, we're at 1. When x is 1, we're at 1/3. What's the domain of the parent graph? The domain is all real numbers. What's the range? All the y's greater than 0. And we have a horizontal asymptote at y equals 0. What is happening in this transformation? Well, there's several things going on. The 2 in front gives me a vertical stretch by 2. So we're going to multiply each of those y values by 2. And then what does the minus 4 at the end do? That moves us down 4. So if I take that 3, stretch by 2, it's going to give me a 6, and then move down 4 steps. Take the 1, multiply by 2, and then go down 4 steps. My domain, again, is going to be all reals. My range are going to be the y's greater than negative 4. Where did I get the negative 4 from? Well, because we went down 4 steps. So my horizontal asymptote gets moved to negative 4. Let's try another one. What is the parent function? The parent is the simplest version, so that would be y equals 4 to the x. I'm going to use that to make my table. When x is negative 1, we're doing the reciprocal, so that's 1/4. When x is 0, 4 to the 0 is 1. When x is 1, 4 to the 1 is 4. So we end up with our parent graph. Our domain is all reals. Our range are the y values greater than 0. And our horizontal asymptote is at y equals 0. That's going to be the same on every single parent graph. Now let's talk about the transformations that we see. What does the 1/2 do? Well, that's a vertical shrink by 1/2. In other words, we're going to take half of all of our y values. What does the minus 4 do from when it's x minus 4? Well, that's going to move me right 4. And the minus 2 at the end moves us down 2. So if we start with 4, take half of it, we're at 2, down 2, and right 4. Half of 1 is a half, down 2, and right 4 puts us here. So our domain is still all real numbers. But since we moved down 2, that changes our range. The y value is greater than negative 2. We have a horizontal asymptote when y equals negative 2. Part D. What's the parent function? Well, the parent is the simplest version. So the parent on this one is going to be y equals 2 to the x. Two to the negative 1 is going to give me 1/2. 2 to the 0 is 1. 2 to the 1 is 2, and 2 squared is 4. What is my domain? All reals. What is the range? The y value is greater than 0. What is the horizontal asymptote? Y equals 0. Notice that that's the same on every parent function, whether it's decreasing or increasing. But let's look at what all happens to this next graph. Okay, this one's got everything. We've got a flip, or a reflection over the x-axis. We have a vertical stretch by 3. We're going up 5. and the x minus 6 is right 6. So I'm going to do a couple of things here. The stretch by 3, so I'm starting here at the 1. Stretch by 3 would bring me to 3. Up 5 would bring me to 8, right? But now I'm flipped, so I'm down here at negative 8, and I'm supposed to go right 6. Stretch by 3, give me to 6. I forgot to flip before I moved up. Pardon that. The flip comes before the moving up. But we do know one thing about that moving up, right? That's going to put our horizontal asymptote at 5. Let's start over. If we start with 1, stretch it by 3, and flip it, we're now at negative 3. Then move up 5 and right 6. If I was at 2, stretch would be 3 times 3, so it would be 6, but we're flipping, so it'd be negative 6, and then move up 5 and right 6. And if you check it in the calculator, you should see something like this. The domain is still all real numbers. We flipped, so this time our range are the y's less than 5. Our horizontal asymptote is at 5. That flip really changes things up, right? So I want you, in your own words, to talk about what each of the things do to a parent graph. What does A do? That's the A in front. What is the C doing, and what is the D doing? I also want you to work through these problems to be prepared for our upcoming Check for Understanding. I would definitely make sure you've practiced 2 and 3.